Hello, mic check. This is day 8 of our daily Putnam challenge while doing some incline push-up. So this looks like it's gonna be a long problem, so I'm gonna read it. This is from Putnam 1989. Evaluate the integral from 0 to a, integral 0 to b of e, maximum of b squared x squared, a squared y squared, dy dx, where a and b are positive numbers. Okay? 1, 2, 3, 4, 5. You know what? I'm gonna write in here on the upper corner the number of push-ups that we've done, right? So that we don't want to go beyond 25. That's just that will exert more effort on our part. But in here, we have a double integral, okay, and our integration region is like a rectangle, okay. So this is a is the x limit, upper limit, and then you have b right here, okay. And so you have an integral that has a maximum, okay. So it will pick between these two values, bx squared x squared or a squared y squared, and which of them is bigger. And intuitively, so you have like when is b squared x squared bigger, or when is a squared y squared bigger. So intuitively in this like region right here, okay, in this lower right corner, okay, in this particular region, x has a larger value while y has very small values. So it follows here that intuitively in this region, this is b squared x squared is greater than a squared y squared. In fact, in this particular point right here, this is a0. You have b squared x squared is equal to b squared a squared, okay, because x is equal to a, while your a squared y squared is equal to 0 in that region, okay, because of course y is equal to 0, okay. And equivalently on this upper left corner, okay, so this, for example, this point let me undo that. This is 0b, okay. On that particular point, we know that the other case holds true. A squared y squared is greater than b squared x squared, and that's because in this particular corner, y has a larger value while x tends towards 0. In particular, this particular point right here for this particular region, your b squared x squared is equal to 0 because of course x is 0 there, while your a squared y squared is equal to a squared b squared, okay. So we know that in regions tending on the upper left region, the maximum would pick out a squared y squared, while on the region going to the lower right, the maximum inside the integrand would pick up b squared x squared, okay. So we're now at 5, 6, 7, 8, 9, 10. Okay, and again we write that down. Okay, so that's the intuitive part. How do we go about making that argument more exact? Well, you can divide this rectangle with a diagonal, okay, and that exactly divides it in the region where a squared y squared is greater than b squared x squared, which is in the upper part of the diagonal, while in the lower part of the diagonal, that's the part where b squared x squared is greater than a squared y squared. And of course that's because this particular diagonal that we pick out has a slope b over a. So this one has an equation b over a x, okay. So that will divide our region. And so what we're gonna do is we will divide our double integral into two separate regions. So let me redraw the rectangle right here so that will be clear. So this is a, this is b, this is the line that divides the two region, y equals b over a x, okay. And so we have here the lower region, okay, where b squared x squared is greater than a squared y squared, and then we have this upper region where the other case holds true, a squared y squared is greater than b squared x squared. And of course in the blue region we will be integrating x from 0 to a, okay. It will run going in that direction. However, going up, y will only run from 0 to the diagonal line. And of course, to the diagonal line, y has a value b over a x. Okay. Consequently, for our in the green region, so let's change the ink of our pen here. We will be integrating y from 0 to b, and then x from 0 up to the diagonal line. Okay, so our limits will be, for the green region, x will be integrated from 0 to, okay, so in the diagonal line, y has a value, x has a value a over b x, and then y, of course, will be integrated from 0 to b. Okay, so that's our integration. So therefore, our integral, which we repeat here, from 0 to a, 0 to b, e maximum between b squared x squared, a squared y squared, dy dx, will be divided into two integrals. Okay, one will be the blue region, integral from 0 to a of the x part, integral from 0 to b over a x of the y part, and then, like we said, in the blue region, the maximum will pick out b squared x squared. Okay, so we have e to the b squared x squared, and then that will be dy dx plus the green region. So let's change our ink to green. Integral, so our y will go from 0 to b. Our x will go from 0 to a over b y. Sorry, this is y. A over b y. Okay, so let's change this here. This should be y. Okay, and then in that particular region, the maximum will pick out a squared y squared. Okay, and so you're integrating dx first and then dy. Okay, so we're now at number 10. Let's do 15. 11, 12, 13, 14, 15. Okay, let's proceed with the integration. So the first integrand, so the integral on dy will be trivial. So you have 0 to a. Since your integrand has no y in it, it's just e b squared x squared. So it looks like it is a constant from the point of view of y. So you'll only have there y e b squared x squared evaluated at b over a x. Okay, so you have bx over a e b squared x squared dx, and then similarly our second term, this time the integral, we're doing the x integral first, and again the integrand doesn't have any x in it. Okay, so it will become x e a squared y squared evaluated at a over by. The lower limit will be gone because it's just 0, so you have a y over b e to the a squared y squared dy. Okay, and then here we can do some substitutions, because look, you have a coefficient of x and then you have e to the some constant x squared. Okay, so when you get the derivative of that, you get the derivative that is proportional to the coefficient x dx, because you have an x already, which is the coefficient of your exponential. So that implies that we can let b squared x squared is equal to u. Okay, that means 2b squared x is equal to du, and then similarly on the second term we can let a squared y squared be something like, let's say, v. Okay, so you have 2a squared y is equal to dv, and then we substitute it back to the integrals. So this is equal to the, okay, let's go blue, integral from 0. So a will now, if x is equal to a, your u limit will now be a squared b squared. Okay, and then you have e to the u du, and then so we need the coefficient we need is 2b squared. We only have a b. Okay, so we need to divide by 2b, so that means the coefficient becomes 1 over 2ab. Okay, and of course the second term is very similar. This becomes the green one, the integral from 0. So when y is equal to b, v is equal to a squared b squared. And again, you have a y, you have an a in there as a coefficient. We need a squared times 2. So we divide it by 1 over 2a. And then you still have a b in there. E to the u, e to the v dv. Okay, and now this integral should be trivial. So we are now at 15, 16, 17, 18, 19, 20. Let's finish it. 21, 22, 23, 24, 25. Okay, so we're done with the push-up. We should be almost done with the integration as well, because here the first term will give you, it's just e to the u, the integral of e to the u. The only variable is the exponential. Okay, so that gives you 1 over 2 ab e evaluated from a squared b squared minus e to the u evaluated at 0, that's just 1, okay, plus 1 over 2ab. So this is a similar integration limits. The only difference is the variable. So the answer should be the same. Is a squared b squared minus 1. Okay, so that should give you e a squared b squared minus 1 over ab. Okay, so this is our final answer right here. Okay, so once again, guys, thanks for watching. I'll see you next time in day 9. Bye bye.